All right, so with regards to homeworks and all of that kind of jazz, so there's a homework number 5 that I put up on Canvas earlier today. That was the one that I was supposed to put up a while back. It's all about BJT circuits effectively. So if we look at it really quickly, that's the wrong thing. Probably should have just opened it up in Word, but it's too late now. So the first problem, you have 2 PNP BJTs, and I want you to analyze the circuits and determine what mode the circuit is operating in based on your analysis. So you're really just comparing quantities VEB to VEC. And so if VEB is greater than 0, it's either in forward active or saturation. If VEB turns out to be less than 0 somehow, it's in cutoff. And then if you compare VEC to VEB, if VEC is greater than VEB, it's in forward active. If VEC is less than VEB, it's in saturation. We've gone through all those relationships. So you're just applying analysis to figure out what those voltages are. Should largely be KVL along the left-hand side, KVL down the right-hand side, solve for the quantities of interest. Then problem 2 is you have I think I called this simple biasing, NPN BJT, where you're asked to determine the DC operating point of the transistor with the early effect neglected, and then in part B with the early effect included. Calculate all that kind of good stuff. Problem 3 is you have the resistive divider biasing network, same basic thing. Figure out what's going on without early effect, with early effect. Problem 4, we have the full resistor bias network. Same thing, figure out what the operating point is with early effect not included and early effect included. So that's what I'm expecting you to be able to do, at least for your calculation problems on your exam. It's all the calculation problems are literally going to be based on the biasing circuits that we talked about. All of the theory questions are going to be on how does this thing work? So expect things about, what does the early effect mean kind of thing? Or does the width of the base region get larger or smaller if the base collector junction is reverse bias? Those type of questions, stuff that we discussed in class. So that's all the BJT stuff that I expect you to know. And then if we go back to home, and then we scroll down here to today's lecture. Here's homework set number 6, due next Wednesday. So a week from today, technically, we're still going to have a little bit more material to cover on this on Friday. But anyway, so here we have a bunch of NMOS transistors, just giving you voltages, and I want you to tell me whether it's in cutoff, saturation, or triode region. Should be pretty easy to figure out. Same basic thing for PMOS transistors. And then we have a bias circuit that we're going to go over today, and I want you to tell me what the DC operating point is when channel length modulation is neglected, and then what the operating point is with channel length modulation included. So it's effectively the exact same crap you did on the BJT homework, but now the early effect is called channel length modulation because it's a different type of device. Same basic thing. And then problem 4, different bias circuit, same thing. Figure out what's going on with channel length modulation neglected, figure out what's going on with channel length modulation included, and then figure out what error is there because you neglected channel length modulation. That is my expectation for you guys for the exam, is to literally just be able to analyze the bias circuits that I've given you, you'll be provided an equation sheet that should have all of the equations for the bias circuits and all of that kind of jazz. But even if I didn't give you an equation sheet, it's always going to be KVL along the left-hand side of the circuit, KVL down the right-hand side of the circuit, set up a system and solve stuff. We're going to go through the MOSFET stuff today, where it's a little bit more annoying because you wind up with polynomial relationships, but I'm going to do all the legwork for you and tell you which solutions don't matter and all that kind of jazz. So from a calculation perspective, the problems on exam 2 are almost exactly what's going to be on the homeworks, except with different numbers. And then on the exams, unless I just give you just a really, really easy softball circuit, channel length modulation and or the early effect are going to be neglected because that makes you have to solve a system as opposed to just apply a damn equation. Okay, so this test should be easy because there's really not a whole hell of a lot of material on it. And then obviously theory questions about how MOSFET works. So that's what's going to be on your test. We are going to cover material and then start an entirely new topic before the test, even if it's on Wednesday. We have that little new material to cover. Okay. So it really doesn't bother me one way or the other whether the exam is on next Wednesday, so a week from today, or the following Friday, because I've already written the damn thing. So I don't have to do any extra work or anything like that. I'll give it to you whatever day you want it, but it has to be one or the other. We can't waste 2 days because amplifier circuits take a lot of time to get through. Okay. I talked a whole hell of a lot. Daniel, did that answer? Oh, wait, no, your question wasn't even about exam 2. It was about when the hell the grades are getting back from examining. All right. So anybody have any other questions about exam 2? Yes.
No, that didn't help.
Okay. Eli, were you raising your hand or did I?
Say that you would be able to get exam before dropping.
So if the exam 2 in-class portion is taken on Wednesday, I will harass the bejesus out of my graders into getting the grades back by Friday. If you take the exam on Friday, there is no way in hell they're getting it graded by Friday afternoon. Just not enough time, and I'm not that much of a slave driver to be like, no, you have to throw away all of your classes and focus on my bullshit. So that's the trade-off. You go into the drop date blind as to what your exam 2 score is. I'm sorry, what was that? I believe I've used a formula sheet and provided a formula sheet for exam 2 in the past. I need to double check that. So if you shoot me an email to remind me, I will look at that after I wrap up my classes today. And if I have one, I will post it online so that you'll have time to acclimate yourself to it. And I'll try to give you a little bit more lead time with the final version of the equation sheet for this test than I did for the first test, where I finished fixing it, I think, a couple of hours before I gave you the test. So can I talk about what we're supposed to cover today now? Okay, I'm just going to do it. All right, so I'm trying to decide whether or not to talk about the small signal model for a MOSFET today, or whether I want to leave that until we're worried about amplifiers to begin with, because it's really not going to have any impact on what we're talking about. So I think I might just literally go straight into the biasing circuits because it'll take a bit to get through all that stuff. All right. So NMOS DC biasing circuits. So the first one that we're going to look at is the 4 resistor biasing circuit with channel length modulation neglected. We're not going to go through simple biasing, resistor divider biasing, and all of that kind of good stuff because we're going to find out that A, this one's going to be ugly enough that we really don't have the time, and B, the equations that we're going to get, you can literally just adapt them to everything else because, for example, if you had a simple biasing circuit, let me draw the full resistor biasing network just really quickly, and so I can explain what the hell I'm talking about here. So here's our resistor at R1. On this side, we have some drain resistor RD. Here's our drain terminal. Here's our source. Here's some resistor RS. Here's our gate. And then here's the resistor R2. While we're at it, here's ID, which we're interested in. VGS, which we're interested in. And VDS, which we are interested in, right? So we're going to develop some relationships for this circuit and all that kind of jazz. Let me put the supply voltage up there because it's going to bother me that I don't have it written down. So this will be VDD. So this is our full resistor biasing network. If we had a situation where we had simple biasing, meaning that the resistor R2 wasn't here, we would just put R2 is equal to infinity into our equation for our full resistor bias network, and it would tell us exactly what's going on. If we didn't have this source resistor right here, where we're degenerating the source terminal with the resistance, we would replace RS with 0 in our equations, and everything will come out just like we had resistor divider biasing for a BJT. So there's really no need to go through all of those other things because we can make one small modification to our equation, and it takes care of all of the different possible ways we could do this. Okay. All right. So one of the biggest pains in the ass of analyzing a MOSFET circuit is that we have to assume an operational mode and then prove that our assumption is correct. Okay. So we are always going to start out by assuming that our device is working in the saturation region of operation, meaning that we are going to assume two things. The first of which is that our gate source voltage VGS is greater than or equal to our threshold voltage. And I'm using VTHN here to designate that this is the threshold voltage of the NMOS transistor. And then we're also making the assumption that our drain current ID is of the form 1/2 mu n Cox W over L times VGS minus VTH squared, or 1/2 K sub n VGS minus VTH squared, where K sub n is mu n Cox W over L. And we'll see with the algebra that carrying all of this through is going to get wildly annoying. So Kn is going to do a lot of heavy lifting today. Okay. So those are our assumptions that we're going to make because these are how the device behaves in the saturation region of operation. Okay. So now we need to figure out what our voltages are and all that kind of stuff, right? Ultimately, we're trying to solve for VGS, ID, and VDS, okay? So what is the voltage at our gate going to be? Right, exactly right. So we don't have to worry about any sort of gate current like we had to worry about a base current in a BJT transistor because we have a capacitor there, right? So at DC, we know that literally no current can flow in. So we have just a very simple voltage divider, okay? So our gate voltage will be VDD times R2 over R1 plus R2. So nothing remotely fancy there. Now we're going to write a KVL equation around this path. And so we are going to see that VG is also equal to whatever our gate source voltage is, plus our drain current times resistor RS. And we can rearrange this to say that our drain current is then equal to VG minus VGS divided by RD. Sorry, RS. My apologies. Thank you for that. Or VDD times R2 over R1 plus R2 minus VGS times 1 over RS. All I've done for the second step here is to substitute in this relationship for VG. So we now have this relationship for ID and this relationship for ID, and they literally have to be equal to each other. Right? So if we set those two relationships equal to each other, we wind up getting VDD times R2 over R1 plus R2 minus VGS. All of this multiplied by 1 over RS is equal to 1/2 times Kn times VGS minus VTHN squared. And we can effectively expand this and move things around such that we get the following polynomial relationship. So doing a little bit of algebra, we have 1/2 Kn RS times VGS squared minus twice VTHN VGS plus VTHN squared minus VDD times R2 over R1 plus R2 plus VGS is equal to 0. And then here I have a polynomial, and it's a second order polynomial in VGS, right? So I have a VGS squared term over there. I have a VGS the first order term here, and then I have a constant term. And so I'm just going to organize this equation in that way so that we wind up getting one half Kn times RS times VGS squared plus 1 minus Kn RS times our threshold voltage times VGS plus 1/2 Kn RS VTHN squared minus VDD times R2 over R1 plus R2 is equal to 0. And so I am going to call this coefficient here A. This coefficient here will be B. And this whole thing here will be C. And then I'm going to use the good old quadratic equation from 8th grade math to figure out what my solutions for VGS are. All right. So VGS will be equal to negative B over 2A plus or minus the square root of B squared minus 4AC all over 4A squared. So all I've done is I've taken the over 2A from the denominator of our normal quadratic equation and just split it out so I could move some of it inside the square root sign. And this comes out to be VTHN minus 1 over KNRS plus the square root of 1 over, excuse me, plus or minus KNRS squared plus 2 over KNRS times VDD R2 over R1 plus R2 minus VTHN. Now, technically, we're getting two solutions here, right? Because we have this plus or minus sign. But as it turns out, this bit right here minus this bit right here is always a negative number. If VGS is a negative number, is our device in saturation? No. So we can literally just throw away that solution because we know for sure it's not going to be the solution that puts us in saturation. Okay. So VGS with channeling modulation neglected will always just be this, determined completely by the parameters of our circuit. So our supply voltages, our resistors that we're using to bias things, our transconductance parameters, that's it. Okay. So once we know what VGS is, we can calculate ID, right? Because ID is given by either of these two relationships. And the only unknown quantity in either of these two relationships was VGS. Okay. So we've solved for VGS. We now have a way to calculate ID. So the only other thing that we really need to be concerned about is the quantity VDS, right? Because for our device to be in saturation, we need, and I did not write this down here, I probably should have, VDS is greater than or equal to VGS minus VTH. Yes, James. No, that's not an equal. That's just a poorly written greater than or equal to VTH. Yeah. Nope, sorry. Greater than or equal to. So we need the device to be capable of conduction. And then in saturation mode, We know that VDS is greater than VGS minus VTH, which gives us this drain current equation. All right, so how are we going to solve for VDS? Kirchhoff's voltage law down the right-hand side. So VDS will be equal to VDD minus RS plus RD times ID. So VDS is already in terms of things that we know once we've solved for VGS. And so we simply compare things, right? So if VDS is greater than VGS minus VTH, we don't have any more work to do because our assumption that saturation mode operation was happening is correct. And so we have effectively found our DC bias point. If VDS is less than VGS minus VTH, unfortunately, we have to redo literally everything, now assuming that the device is operating in triode region. Okay, so that's our check. If VDS is greater than or equal to VGS minus VTHN, then the saturation mode assumption was correct. If not, assume triode and start over. So let me take my original circuit here. And now we're going to analyze it in triode mode. So what does triode mode operation look like? Well, we know that VGS will still be greater than or equal to VTH. We also know that VDS will be less than or equal to VGS minus VTH. And our drain current will be mu n Cox W over L times VGS minus VTHN times VDS plus 1/2 of VDS squared, or Kn times VGS minus VTHN VDS plus 1/2 VDS squared. Our analysis is going to effectively be similar here, right? So from the jump, we can easily see that VG is still VDD times R2 over R1 plus R2. Then we have VGS is equal to VG minus ID times RS. So that's just KVL around that blue path and then rearranging things a little bit. If we substitute in our relationship for our drain current, this looks like VDD times R2 over R1 plus R2 minus KN RS VGS minus VTHN times VDS. Oh, shit. That's supposed to be a minus sign, my bad. Where'd it go? So all I did to go from here to here is literally substitute in the relationship for VG and substitute in the relationship for ID. And we have a single equation with two unknown quantities, right? So we don't know what VGS is and we don't know what VDS is. So now we're going to have to write our KVL equation down the right-hand side in order to figure out what's going on with VDS. So once again, we'll see that VDS is equal to VDD minus RD plus RS times ID. Substituting in our relationship for ID, we get VDD minus KN RD plus RS times VGS minus VTHN times VDS minus 1/2 VDS squared. So here's equation 1, here's equation 2. So now we have a 2-equation, 2 unknown system that we can solve for VGS and VDS. And once we know both VGS and VDS, we can plug them in up here to solve for our drain current, and we've determined our DC operating point. So that's what things look like without channel length modulation. So this is the easy thing. All right, so I'm going to ask you guys a question I think I know the answer to already, but I'm just going to ask it anyway. Do you want to see a numerical worked out problem, or are we good? Okay. Fair enough. Okay. So here's our example. Our supply voltage is 1.8 volts. Here we have a 4 kilo ohm resistor, a 3.5 kilo ohm resistor, a 500 ohm resistor, ten kilo ohm resistor, here's VGS, ID, and VDS. And we're told that our transconductance parameter Kn is 1 milliamp per volt squared. So this is a rather large MOSFET. Our threshold voltage is 0.4 volts. And our channel length modulation coefficient is 0, so that we can neglect channel length modulation. Okay. So the first thing that we are going to do, We always start out by assuming the device is in the saturation mode of operation, which means we just get to apply an equation that I've given you. Yes, Jacob. So let's look back at these equations here really quickly to answer that question. If we assume that the device is in saturation mode operation, we have a definite numerical expression to get VGS, IV, and VDS. If we assume it's in triode first, we have to solve the system of equations in order to get things, which I argue is more of a pain in the ass than just applying an equation. So that's why we're going to assume saturation first and hope to God we're right. We won't. So our equation, and this is what was written down earlier, is our gate source voltage will be VTHN minus 1 over KNRS plus the square root of 1 over KNRS squared plus 2 over KNRS times VDD R2 R1 plus R2 minus VTHN. Let me extend this square root sign like so. And if we plug in our numbers, we wind up getting 1.146 volts. And if any of you guys want to pull out your calculator and verify that, go nuts. So using this number, we can then see that the quantity VGS minus VTH is 0.746 volts, which means we've confirmed our device is on properly. Okay. Our drain current, ID, is given by 1/2 Kn VGS minus VTHN squared, will come out to be 278.576 microamperes. And our drain source voltage VDS given by VDD minus RD plus RS times ID comes out at 0.686 volts. So is this device in saturation or not? No, because VDS is less than VGS minus VTH, right? So those are the two figures of merit that we are comparing. If VDS is less than VGS minus VTH, then our assumption of saturation mode operation is incorrect. Ryder, how may I help you? So if VGS minus VTH is positive, it's on. Yes. Are we expecting to derive it? No. Good Lord, no. No, I tried to do the hard work for it. Just apply it. Gabriel. Yes. I have to give you the threshold voltages. I have to give you the transconductance parameter. Yes. What do you think? If it's got an NMOS transistor, absolutely. If it's got a PMOS transistor, not so much. So when we cover PMOS on Friday, I'll give you those equations on Friday. You can have lots of gross absolute value signs all over the damn place. Largely the same, but a couple of things. All right, so Are we all on the same page that VDS 0.686 volts is less than VGS minus VTH 0.746 volts, which means our saturation mode assumption was wrong. All right, so bad news. So assuming triode operation, now I've already given you the two equations that we set up our system with, right? So our first equation, VDS is equal to VDD times R2 over R1 plus R2 minus KN RS VGS minus VTHN times VDS minus 1/2 VDS squared. So that's one equation. Our other equation, VDS is equal to VDD minus KN RD plus RS VGS minus VTHN VDS minus 1/2 VDS squared. So there's our two equations, and now we're going to solve that system. But wait, it becomes more of a pain in the ass. How, you say? Because VDS is squared here, which means we're also going to have two solutions, only one of which is actually going to give us triode mode operation. So not only did we find out that our saturation mode assumption was wrong, now we have to do even more work to make sure that we get the right triode mode operation equation or solution, okay? So we have two solutions. Solution number one. We find that VGS is 1.147 volts and VDS is 0.690 volts. And then over here, we have solution number two, where we get VGS is equal to 1.278 volts and VDS is 1.738 volts. Which of these is the right solution? Right, the one where VDS is less than VGS minus VTH. So over here on the right, we can very obviously see that VDS is greater than VGS, which means it's definitely going to be greater than VGS minus VTH. So that can't be the correct solution. So this must have been the correct solution. So plugging those numbers in, we find out that our drain current ID, KN, VGS minus VTHN, VDS minus 1/2 VDS squared, comes out to be 277.408 microamps. And so now we have completely defined our DC operating point because we know VGS, we know the VDS, we know ID, and all of our conditions for triode have been met. Yes. Oh, damn it. Thank you. This first one is VGS. Thank you for that. Wrote down the wrong subscript there. Thank you. All right. So let's make this more difficult by including channel length modulation. Yep. So the supply voltage in a BJT is VCC because it's the voltage at the collector that's applied effectively at the collector terminal, so the highest point of potential. In a MOSFET, it's typically VDD because we apply the highest potential at the drain side. That's it. That's literally it. So VCC for BJTs, because in a NPN BJT, the collector is at the point of highest potential. VDD for N MOSFET because the drain is at the point of highest potential. I don't know why they came up with that, but that's all of it is. Yes.
Whenever doing that, if you do this, like this, how do you do it? How do you do it?
So, I don't know that your calculator can solve that system with a two equation, two unknown solver because it's a quadratic system, which means realistically it's a computer problem. So on an exam, all I can do is ask you, is this transistor in saturation or not? Yep. Yeah. So you can do a whole bunch of work to say it is in saturation or it is not in saturation. And then if it is not in saturation, you have to stop there unless you've got a computer in front of you. Yes, ma'am. So VTH is just generically the threshold voltage. VTHN is the threshold voltage for an NMOS transistor. That's all that little subscript means there because we're about to start working on stuff that has both NMOS transistors and PMOS transistors at the same time, which means we're going to have two threshold voltages to worry about. And so I'm just already getting your brain primed for seeing the difference between these. That's it. You said gross, you're correct. Any other questions about this one before we move on to actually making it difficult? Yeah, I know, I'm a jet. All right, so same basic thing, but now include channel length modulation, right? So that means we're going to assume saturation from the jump. So VGS must be greater than or equal to VTH. VDS must be greater than or equal to VGS minus VTH. And our drain current will be 1/2 Kn times VGS minus VTH n squared times 1 plus lambda VDS. So inherently, VGS and VDS are always going to be effectively tied to each other, so we're going to wind up with a system. So, not going to write down what VG is again because it's the same thing every damn time. VD times R2 over R1. So we can solve for VGS by writing a Kirchhoff's voltage law equation around that bottom loop that I've done in blue. And so we get VGS is equal to VG minus ID times RS. Substituting in our relationships for VG and ID, we get VDD times R2 over R1 plus R2 minus 1/2 Kn RS VGS minus VTHN squared 1 plus lambda VDS. Applying KVL to the right-hand side of the circuit, we get VDS is equal to VDD minus RD plus RS times ID. Is equal to VDD minus 1/2 KN RD plus RS VGS minus VTH N squared 1 plus lambda VDS. So once again, we have a 2-equation, 2 unknown system. If VDS is greater than VGS minus VTH, our assumption is correct. If VDS is less than VGS minus VTH, then our assumption was wrong. And then we have to work the problem in assuming triode region of operation. That being said, triode region of operation isn't really any worse than this because channel length modulation does not exist in the triode region of operation, meaning we can just use our previous equations and go from there. So these are all of the different ways that the 4-resistor bias network can bias in the X effectively, right? So without channel length modulation in saturation mode, things are fairly straightforward. Literally any other thing, so triode or with channel length modulation included, we wind up having a system of equations that we need to solve, which means it's computer science. Okay. So I were you, I would do like I did and literally set up just a MathCAD sheet for just chugging through these things where you just plug in the resistor values and let the computer do all the work things. Or you could write a MATLAB program that does the same thing. Whatever will float your boat. If you're going to be doing enough of this, having a template to just burn through it quickly is going to be a beast. All right, so this is our first bias network. Now let's look at a self-biasing network. And once again, we're going to have to do this with and without channel length modulation. Hopefully we have time to do both today, but if we don't, it'll be all right. So this is effectively the exact same thing as the self-biasing networks for BJTs. So here we have our supply voltage VDD, some resistor RD. Here I'm going to have some gate resistance RG. Here's some resistance RS. So here's VGS. This is ID. Just to remind you, this is also ID. And here's VDS. So what's the relationship between VGS and VDS in this circuit? How is VGS and VDS related to each other? Laimi, I believe, just said that they are the same. That's true. VDS and VGS are literally the same because there can't be a voltage drop across all resistor RD because there's no current flowing into the gate capacitor there. So if VGS and VDS are the same thing, this device must always be in saturation because VDS will always be greater than VGS minus VTH because VGS is always greater than VGS minus some number, right? So if it's working at all, it's in saturation. So there is no triode that we have to worry about or anything like that. Okay? So always in saturation. VDS is equal to VGS, which means VGS is always greater than, VGS greater than or equal to VTHN, and ID will be 1/2 KN VGS minus VTHN squared, and then when we have channel length modulation, we'll just add the 1 plus lambda VGS there on the side, right? Okay, so if we write a KVL equation down the right-hand side of the circuit, what we wind up getting is VGS is equal to VDD minus RD plus RS times ID, which we can rearrange to find that ID is equal to VDD minus VGS over RD plus RS. We set our two relationships for the drain current equal to each other. We wind up getting VDD minus VGS over RD plus RS is equal to 1/2 KN VGS minus VTHN squared. And we can expand this to get 1/2 KN RD plus RS times VGS squared plus 1 minus KN RD plus RS times VTH. Sorry, that should be a square bracket. Times VGS plus 1/2 KN RD plus RS VTHN squared minus VDD is equal to 0. And once again, we have a quadratic equation and all of that kind of stuff. Solving this quadratic equation, we wind up getting VGS is equal to VTHN minus 1 over KN times RD plus RS plus the square root of 1 over KN times RD plus RS squared plus twice VDD minus VTHN divided by KN RD plus RS. All of that is under the square root sign. And then once we know what VGS is, we can use this relationship or our other relationship to find ID. So with channel length modulation included, literally the only thing that's going to change is this relationship right here. right? VGS will still be equal to VDP minus RD plus RS times ID, but now we're gonna have that 1 plus lambda VGS term there, right? So with channel length modulation included, we wind up getting VDD minus VGS over RD plus RS is equal to 1/2 KN VGS minus VTHN squared times 1 plus lambda VGS, which is a third order polynomial in VGS. Only one of the three solutions will be a positive number. That's the correct one. So that's DC biasing of NMOS circuits, right? So we have literally just two different circuits to worry about. The 4 resistor biasing network, which we can modify to look like any of the other networks. So like simple biasing, resistor divider biasing, etc. And then we have our self biasing. Yes. Okay. Sure. Right. So it's always 1 plus lambda VDS, but in the self-biasing circuit, VDS and VGS are the same thing. So that's why I substituted in VGS there, so that I only have the one variable to solve for. Okay. So channel length modulation, I guess I don't really understand your question, like, so channel length modulation is going to be more prevalent when you have a short channel device than when you have a long channel device. Because channel length modulation effectively describes the change in the relative length of the device, right? So that's what that parameter gamma looks like. So if you have a very long, did you guys not watch the video? Well, that will screw a lot of stuff up. If you go back and watch the video that I suggest, or that I put up there for you guys to watch, only the last half hour of it really is talking about saturation mode and then channel length modulation, but effectively just a super crash course in it because you didn't watch it and we've got 10 damn minutes. So guys are killing me. Here is my N plus implant. Here's my N plus implant. That's my oxide layer. Sorry, this should be VGS minus VTH. Let's not worry about the end thing. Okay, so this is the situation that we're starting, okay? So we're definitely in saturation mode of operation because VGS is greater than or equal to VTH, which means we have a conducting channel here, and VGS is greater than or equal to VGS minus VTH. So when VGS is exactly equal to VGS minus VTH, our charge distribution profile looks like this. So we have that linear relationship that we saw earlier when VGS was less than VGS minus VTH. but the channel becomes pinched off. So effectively, the depth of the channel is 0 on the drain side. And that's what happens when VDS is exactly equal to VDS minus VT. If we allow VDS to be greater than VDS minus VTH, the pinch off point occurs further in the channel, right? So effectively, instead of it being pinched off right there, it might be pinched off right here. So that we have some, so if this is X is equal to 0, and this is the X direction, we have some effective length that is smaller than the actual length of our channel. And since we know that our drain current is 1/2 mu n C ox W over L times VGS minus VTH squared. When that L gets smaller, we should see an increase in our drain current. We're going to see a linear increase in our drain current. So instead of our saturation, our drain current in saturation being completely independent of VDS, we should see that it scales linearly with VDS. Now, we take into account this scaling with the quantity 1 plus lambda times VDS, where this lambda parameter is the channel length modulation coefficient. And all it's saying is effective, like it's a ratio of the relative length of the channel to the actual length of the channel. So like how it scales. So if we have a very long channel, our channel length modulation coefficient is usually very small because it takes a really large VDS in order to make any impact on where the pinch off point is. Whereas if our channel is very, very short, a relatively small VDS voltage can cause a large change in the effective length of the channel. So it's not something that we get to choose whether or not we have. It's just something that we choose whether or not to ignore. It's always there if we're driving, if our VDS voltage is greater than our overdrive. It's always there. It's just whether or not it actually has any significant impact is the question. So for long channel devices, typically speaking, we can ignore it because this parameter is going to be very, very close to 0. For short channel devices, this parameter is going to be significantly larger. Yes. So simple biasing. Well, so it depends on whether or not we are going to have source to generation or not, right? So for example, if we had a circuit, let me draw it out. So we might have something like this. So in this case, R2 is infinity and RS is 0. Let's look up here. This is where we started. No, here's where we started. So all right. So we're looking at this relationship here for VGS and all of this kind of stuff, right? And the issue that you're saying that we have is that RS is 0, which means we have VTH minus effectively infinity plus this thing over here, which is the square root of infinity squared, and then we've got an infinity thing here, all this here. I would argue that if we look at this damn thing, this is the VGS that we're trying to solve for, right? What's the voltage drop across the resistor R1? Nothing, because there's no current flowing through it, which means VGS is VGT. Yep. Because VGS is VDD, VDS will always be less than our gate source voltage. Because VDS is taking into account that there's a voltage drop across this resistor RD. So we're likely always going to be in the triode region of operation with that particular configuration. Technically, it depends on what our threshold voltage is and what our supply voltage is, but I would be willing to, I can say pretty definitively here that the overwhelming majority of combinations of supply voltages and all that kind of stuff are going to wind up forcing you into triode here, unless RD is just very small so that there's not an appreciable voltage drop. But finding VGS is pretty straightforward for this. With the RS resistor there, it's, like I said, just treat R2 as if it were infinity, which means up in this equation, where we have VDB divide or times R2 over R1 plus R2, that's literally just going to be VDB minus VDHN. So we're effectively saying, yeah, VDB, that goes to 1, and that's the only thing that needs to be done. I'm just trying to think if I've seen that particular configuration actually used, and usually the answer is no. So like, without this particular resistor right here, so with this as an open circuit, this configuration is what's very commonly used to bias what are called source follower amplifiers, which is effectively the MOSFET version of a unity gain buffer, or as close as you can get to it. So we should see that the gain on this is positive, and it's usually very, very close to 1, usually somewhere in the ballpark of 0.9 to 0.95, depending on what the parameters are and all that kind of good stuff. But I've never seen a source follower where you did not have a source resistance right here, because the generation provided by the source resistance gives us the nice stable operating point and all that kind of good stuff. Yeah, I mean, you can set one up like that. Like you can go get a MOSFET out of my office and burn one out or whatever, trying to set it up like that. It's just going to have a really, really large, like I said, gate source voltage, whatever VDD is. And so it's going to try to push a whole hell of a lot of current through it. So probably wind up burning it out, but nothing physically stopping me from doing it, and see what happens. All right, we're 2 minutes past time, so I'm going to go get ready for my next one.